Hello and welcome just to a bit of an improv video. Today we are going to be computing the integral of this infinite sort of summation, you could say, of natural logs of x's, and we are going to use some basic techniques of manipulation of functions and integrals to do this. So let's go ahead and start off by manipulating our definition for y here. So y is equal to natural log of x minus the natural log of x minus the natural log of x minus the natural log of x infinite times. So from this, what can we do? Well, embedded in this function is itself. So we can identify that this is basically itself, the definition of the actual function. So what we can do is we can allow y to equal the natural log of x subtracting y. And that is a very, very nice thing that could help if we were dealing with surds or something like that. But if we wanted to find an equation for y, how would we go about doing that? Or at least find a integratable function. The first thing we would want to do is rearrange to have y on one side and x on one side. So we could make a function of x in terms of y instead of a function of y in terms of x. So to do that, we just take the exponent of both sides, e to the power of that thing. So we have e to the power of y and e to the power of natural log x minus y, which cancels out. So e to the natural log of x minus y, and that allows e to the y to equal x minus y. And now we can just add y to both sides. E to the y plus y is equal to x. And now we can actually begin our manipulation of our integral somehow. And that is actually a pretty simple task here. All we can do is find dx dy. And that can help us find an integratable term that we can easily integrate with some techniques that we know. And that actually helps us find the answer. So we just find dx dy. Dx dy in this case is going to be e to the y plus 1. And that's actually the derivative of the x function in terms of y. You could flip it, take the reciprocal, and find the dy dx function, but that we do not need. But that could be useful in finding the derivative of this infinite sum. So let's go ahead and let's find dx. This can help us here with our definition right here. So to do this, we just multiply each side technically, or integrate both sides by y. And what this gives is dx is equal to e to the y plus 1 dy. And now we can actually substitute this directly into our integral. So into the integral, hopefully you guys can see this okay. I've just been having some problems with filming using this, so hopefully you guys can see this fine. So into the integral, we get the integral of y multiplied by this stuff, e to the y plus 1 dy. And now we can use integration by parts. And we can just expand this first before doing that. Y e to the y dy. Because the integrals are additive, we can split them from one another. So we get 1 dy. Sorry, that's supposed to be y because we expanded the y. Y dy. Perfect. And now we can use integration by parts to find this first term. So by integration by parts, IBP integration by parts is equal to the derivative, the integral of e to the y, so y e to the y minus the integral of, we'll take the derivative as the derivative of y, so we derive y and we get 1, so we just get the integral of e to the y dy, and that's just equal to y e to the y minus e to the y, and when we add them together we will add the constant of integration. And obviously we know how to integrate a basic polynomial here. That's just y squared over 2. And now we can add them together and add a constant of integration. Hopefully, again, you guys can see this. So we get y e to the y minus e to the y plus y squared over 2 plus the constant of integration. Now we wanted to find an integral in terms of x. So what we can actually do to find this is we can just substitute back in our infinite function. So this is going to be quite ugly. So the integral of the natural log of x take away the natural log of x take away the natural log of x, so on, dx is equal, so our y was equal to that stuff, the natural log of x, take away the natural log of x, take away the natural log of x, infinitely, multiplied by e to the power of this, so we just multiplied by x, take away the natural log of x, take away the natural log of x, take away the natural log of x, so on, infinite series there, infinite sum, sorry, whatever you want to call it, infinite function. And again, we just subtract the same thing. It's not multiplied this time though. So we just go x minus the natural log of x minus the natural log of x, and so on, so forward. And we add y squared over 2 as well. So we get the natural log of x, take away the natural log of x, take away the natural log of x, and so on. All divided by 2, and that is squared. Okay? And of course we have our constant of integration. And one example we could look at to prove that this method works is y is equal to x squared. You can do it with basic functions like that. So henceforth you can do it with continuous functions like this. And, you know, finding the definite integral of a function like this would be very difficult because you're taking a point of infinite points, sort of, it's sort of hard to explain. Like, if you wanted to evaluate this at 5, for example, then what would the value be? It would be infinitely counting, you know? So it would be quite difficult, and I challenge you guys to try and like find something like from 0 wouldn't be defined. From 2 to 3, for example, what would the value be? It would be quite interesting to find. I might do that in another video, but that is it for this video. I hope you guys enjoyed it. I am new to these math videos. I only have 2 subscribers. I don't really care about subscriber count, but it would be nice to get a few people interested in these videos, just so I can continue to make them. So guys, I hope you guys enjoyed this video, and I'll see you guys in the next one.